Glad to be here. I work from Intel. As you know, we do chips. That probably is not a secret. But it's probably a secret we actually do software as well. So I'm actually from the software team, and we got a chance to work with the hardware architects very closely in terms of designing the chip, as well as optimizing for the chips that we do here. So it's, we have more than 10,000 software people actually at Intel here. So what I want to talk to you today is about software chips, and our end goal, obviously, is performance. So three things were mentioned today here. Now, it's great to go after the other speakers because some of these things I mentioned already, right? Dimitri mentioned the pillars of deep learning. There are three things that are important, and in terms of compute, as well as data, as well as algorithms here. Within Intel, we are just like everybody else. We're very excited about AI, and we want to develop the best chips for this. Now, on the other hand, I agree with Dave that nobody really knows which design will win, right? Is there going to be customized chip in a certain way, or is there going to be GPU, is it going to be CPU? Actually, we are doing all of these things here at Intel. When you think about AI there's a question earlier about AI from the edge side as well as the server side. We're developing chips across the board. So for example, on the edge side, we have a custom chip, which is a design for computer vision only. Actually, it's very low power. We actually have a booth outside. You will get a chance to take a look. We build a neural compute stick. It's very small, where actually it will do the computer vision and the deep learning inference. So that's the one end of it. And the other end of it, we obviously have CPUs. On the server side, we have these CPUs that are capable of doing all kinds of workloads. It's a general purpose. You can run all kinds of things you want. Then on top of this, you can run deep learning as well. So in addition to chips, let me show you something a little bit different. So Dave mentioned in 2015, when he compared between TPU1 and CPU didn't really look very good, right? You saw the chart where the CPU performance was really at the bottom here. And we, at Intel, realized there was a problem here. So about 3 to 4 years ago, around beginning of 2016, we started looking into the issue to see what can we do to get better performance on the CPU side. So we had a team working on these things. My team started working on various different optimizations for software. I want to see how much of this was due to the hardware side and how much of this was due to the software side. And to our surprise, the software at that time, they were all open source frameworks. They were not really well optimized for CPU here. Okay. So we worked on this for about 1.5 years. During July of 2017, we actually saw performance gain of about 50x. So we compared between the baseline software. This is actually Café using ResNet 50. Baseline software on the platform we have at that time versus the optimized version of our software in July 2017, we saw 50x performance gain. And then we did not stop. We continued to optimize our software. And then over time, we measured again about a month ago, in February 2019, we improved performance again by around 5.7x. So the total performance gain was roughly 285x. Now, what does that mean when you have such a performance gain? Just let me show you how that feels like. Is it showing here? I guess the video is not showing here. Exit presentation mode, and I cannot show the. Okay. Wow. All right, so, and I cannot do the link here. Let me just go to, sorry. Let me just do the manually here. All right. Okay, so on the left-hand side was the baseline software. And you can see it is actually not very fast, right? And then on the right-hand side is the software we have optimized. And you can see that it's really a meaningful difference when you have more than 200x performance gain using software alone, okay? So what does that mean when software can make such a big difference here? Dave alluded to a little bit earlier also. Software actually may be the big thing that people just don't talk about, right? So when we have all these startups, people design all kinds of chips, what they show you tend to be the peak performance. They show you the peak flops you have, whatever teraflops you have at the peak, right? But if software can swing performance by 200x, then if your hardware has 2x more flops, it really is in the noise, right? So it's key, so we actually want to improve performance on the software side to make sure software is really well map the algorithms to the hardware you have here. So the job, as I mentioned earlier, is to map the topologies and the underlying hardware. So let's understand the topologies a little bit better here. Now, Reza mentioned he loves computer vision, but he wants more than computer vision also. And we are seeing the field is changing. So when, in 2012, when this field just got reinvigorated at that time, it was all because of computer vision, right? It was ImageNet. You're able to recognize whether something is a cat, whether something is a dog, right? It was a huge deal. And we went through the AlexNet, we went through, nowadays, everything, whenever we talk about deep learning, we have to talk about ResNet 50. So I had a ResNet 50 slide also. So that was the beginning of deep learning. But over time, things have evolved quite a bit, actually. You not only have computer vision side of algorithms, we also go into the RNN side where you actually do speech recognition, NLP. And then the other thing which is interesting was the recommendation system. When I talk to the cloud service providers, quite often they say, we like computer vision, we like speech, they're all very important to us, but the number one application in terms of burning the amount of cycles is actually recommendation system. That's where they actually rank how important these items are, right? And we also saw something like reinforcement learning coming back. And there are different ways of doing reinforcement learning, and there are different approaches of doing this, and that also has implications on the underlying hardware here. So let me understand a little bit more about how these applications, so from system software and hardware perspective, these are all sort of workloads for us. And our job really to make sure we can run these workloads well through software optimizations and through hardware we have here. So if you look at, actually Dave mentioned, it's great I'm going after all these guys. He mentioned the roof-run analysis and the compute arithmetic intensity, right? So something like CNN, the compute intensity is very high, okay? And the x-axis is the number of data references, and the y-axis is the number of compute you have on top of these references. So you can see you have a large amount of compute for the amount of data references you have here in terms of data load and store here. Now, if you look at something like RNN, they actually look very different from CNN, right? So from RNN perspective, these are the red dots. The blue dots are the CNN, the red dots are the RNNs. And from an RNN perspective, you can see they are much lower now. They have low intensity. So when you have the amount of data they touch is not really very large, but the amount of reuse you have is actually much smaller than the CNN side. Now here's another example, which is NCF. That's a recommendation system I mentioned earlier. It is a proxy for the all kinds of recommendation systems the cloud service providers are doing there. And what you can see here is these are green dots, and they're actually very spread around. And some of these dots have high arithmetic intensity. Some of you have these dots have a very, very low compute intensity here. Okay? Now, this is another example called MiniGO. It's actually one of, actually both, so I've gone through 4 examples here. 3 of them are part of MLPerf. And these are 3 examples. We did a submission for 3 benchmarks to MLPerf. And the MiniGO looks also a little bit different from the RNN and CNN side. If you look at the left-hand side, a big chunk of time is spent on simulation tree search, and a reasonable chunk is spent on conf, and actually relatively small amount is spent on training. It's roughly 14%. Okay? So you may have noticed if you compare between this and the CNN slide, CNN, majority of that is spent on conf, right? 99% of the time is spent on different types of convolutions here. So in terms of computation, things have changed from one type to the other. Now, that's interesting from both the system software and hardware perspective, because if you want to customize, so somebody earlier asked the question, can you do a customization for one or customization for the other, right? So if you do customization for all of these, and then you get to work, you have all kinds of accelerators. And maybe that's what you need, and maybe that's not sustainable from an economic perspective to develop a custom chip only for one particular application here. Okay, so what do we do inside software, and how do we get better performance here? Within Intel, our job is to do actually 2 types of things here. So one is we want to enable what we call the software ecosystem, right? We want to embrace the existing frameworks out there. So PyTorch, mentioned just before me, and TensorFlow, Caffe, all these popular frameworks, we want to make sure these are all well optimized on Intel platforms. And that's one part of our job here. And the other part of our job is to make sure we have enough of these for our business. So we actually created a few additional software tools or frameworks for deep learning. So one of them we have created is called BigDL. And as you probably know, if you are coming from the enterprise side, Spark is very popular. A lot of the big data is actually inside Spark. And in order to do deep learning on Spark itself, you don't want to get the data out and do work and then move back. You want to be able to natively do deep learning on Spark. And that's how we created something called BigDL to allow you to do native deep learning inside the Spark environment. And then the other thing we have done is we have developed a software toolkit for computer vision only called OpenVINO. Actually, outside the booth, they are demoing the OpenVINO on the neural compute stick that I mentioned a little bit earlier. And I was told they're giving the stuff away. So if you hurry up right after this talk, don't do it now. And you can probably grab one of these neural compute stick over there. Right? Now, in order to optimize well that entire layer of software, right, from platform, from a framework perspective to toolkit and so on, we developed the underlying libraries. So there are 2 things that are important here. One is deep learning eventually is going to be really matrix of computation, right? Everybody's building matrix compute sort of units there. And luckily, Intel has been in the HPC field for a long time. And we are one of the top providers in the supercomputing business. And we have something called MKL, math kernel library. So we extend the math kernel library to handle the additional primitives required for deep learning. And we actually made this is called MKL-DNN, and that's actually open source. You can download, you can go out on the GitHub and download from there. And then the other part of this is communications. Particularly for training, you want to scale out to hundreds of nodes and thousands of nodes. And in order to efficiently do communication for deep learning, we have created a new library called Machine Learning Scaling Library. And that one is open source as well. You can get it on the over there. Okay. So let's look at how we do these software optimizations on the variety of architectures Intel is developing. So I will give you just two examples here for the short of time here. I want to give you the two ends, as I mentioned earlier. One end is the very low power custom chip designed for computer vision only. And the other end is the general purpose compute, which is CPU for deep learning as well. And as I mentioned earlier, we also do all kinds of other chips in between, where we do customized chip for deep learning inference in the cloud. We also do custom chip for deep learning training inside cloud as well. So we have a variety. We do FPGA as well. We have a variety of things going on here. But I'll just talk about two examples here. The VPU, the Vision Processing Unit, it's probably not surprising to you in terms of what kind of capabilities we have here. It is very similar. You need it's low power, and it has a neural compute engine, which does matrix multiplication and so on, convolution and so on, right? And then we also have VLW processor cores on the side, where if it's not matrix multiplication kind of thing, that you actually you use other processing units for this. Okay? So from the software perspective, what you need to do is to figure out a way to schedule. It's basically you have a heterogeneous environment underneath you. So you want the software to be able to place and schedule various operations on the various different units here. You want to schedule the tensor operations, the matrix operations on the matrix core, and you want to schedule the other stuff on the VLW core here. And the transformation you're going through will be something like tensorization. And what's interesting is, so my background was also from the HPC side years ago, right? So I did my PhD thesis on compilers for supercomputers. And my particular topic was loop nest optimizations for matrix computation. Okay? So in order to do well on the supercomputer side, you had to do things like loop interchange and blocking, all of these things. And it's very much the same technologies you have to do here in order to get best performance. So when you do tensorization, you really need to create a block and make sure that computation will fit into the memory, the matrix compute unit here. Now, let me show you a different example here. So this is on the CPU side. As I mentioned, CPU is general purpose computing, right? But people probably don't know is inside CPU, we have a lot of compute capability as well. And there was a question earlier, why not just add another matrix thing inside CPU, then you can do the same thing here, which is exactly what we're doing, actually, marching towards. So between what Dave mentioned in 2015 on the Haswell machine, which was 3 generations old, and to today, we have increased the compute capability quite a bit. In our current generation, which is called Skylake, that has a very wide vector computation, and that can be used for speeding up deep learning matrix computations. And then actually, next week, we are doing another launch of a new generation of CPU, and that CPU has additional features for design for deep learning, something called DL Boost, and that will give you integer 8 capabilities. So this is more than just FP32. we're doing integer 8 as well, particularly important for inference. And we will show, I actually gave a talk last week, but we cannot talk about numbers today because the launch is actually next week. So if you can wait until next week, you get to see all kinds of different numbers. We have very, very strong numbers coming out of the next generation CPU there. Now, moving forward, we also announced last year, inside CPU, we're going to develop the additional matrix capability as well. So we have something which actually will do the tensor operations inside CPU, but that will be coming out in the future generation. So how do you, want to make sure I'm on time here. So how do you get performance out of this, out of CPU? As I mentioned, the CPU today has a very wide vector. So you can use these vector units to get better performance here. And CPU in the future will have these matrix operations here. So in order to get these vector performance out for deep learning, usually, and also the other thing CPU has is we have many, many cores, right? So a Skylake machine has 56 cores already. And going forward, you will have more cores. What we'll be announcing next week, we'll have more cores. So you think about one CPU node has a lot of cores in it already, and each core has these strong vector units in it, right? So in order to get the best performance there, it's like you do, you do programming for supercomputers in the past, right? So there are really three things that are important here. One is you find the places where you can do parallelization, because there are multiple cores here. You want to parallelize in a certain way and making use of all the cores here. And the other thing which is important is each core you want to vectorize well. So you find these matrices where you can do the right vectorization. And then on top of this is data locality is going to be super important, right? And that's where all the blocking, all of these things will come in to make sure once you bring the data in to our cache, and then you can just make use of that inside, make use of data inside cache here. Now, as I mentioned earlier, we did submit our results to MLPerf during the MLPerf 0.5 time, which is late last year. So we had 3 submissions here. One is ResNet 50, I mentioned already, and then the set number 2 is NCF, which is a recommendation system, and the last one is MiniGO, which is reinforcement learning. They represent sort of a variety of workloads inside deep learning today. On ResNet, so the baseline, the MLPerf baseline is a GPU performance, is a P100, not the latest GPU, but the P100. And the scores look, and our system is not the latest CPU either, right? So I just want to give you a feel for, in terms of what is the gap between CPU and GPU today. If you have a P100, so ResNet 50 is 15% away from P100 baseline. And NCF actually is 60% faster than that particular version of the baseline there. And MiniGO, actually we are the only company that submitted MiniGO. and MiniGO, we are, on the CPU, we got a score of 6.3, which means it's 6x faster than the underlying baseline. Now, I mentioned earlier, not only single node performance, you also want to go multi-node. And because of the techniques we have developed inside, not only the frameworks, but also the library, MLSL, we're able to see very good scaling out of multi-node here. And this is what my team measured, which is measured on, just grab the instances on the AWS cloud, and we're able to see more than 90% scaling up to, all the way to 128 nodes. And other people have done much larger measurement than us. So we've seen a research lab called ServSera in Europe. They actually had access to a supercomputing center in Spain. They scaled this to 600 CPU nodes and got more than 90% scaling over there. We also have seen even bigger numbers people have tried. So for example, UC Berkeley, I was actually at Berkeley a few days ago. Their team submitted to another supercomputing center in UT Austin, where they measured Resnet 50 on 1,600 processors, right? And we also had a collaboration between Intel, Stanford, and NERSC. They had an application where they scale all the way to 9,000 nodes. So there's a variety of people looking at the large-scale deep learning, and it's been very interesting to see these numbers. How much more time do I have? 5 minutes? Okay. All right. So, so at the end of the day, it's the customer cases are what actually matter. Eventually, we're a business. We're here to serve our customers and make sure their workloads can run well. So what I want to show you is a few examples out of these customer cases here. So in the past about 2 years, we have been working with a lot of people. Okay? So we have our sales guys doing a fantastic job. They've been looking at getting design wins. They've been talking to their customers, and many of these the cloud service providers and a variety of people we actually talk to there. So I'll just pick a few examples here, 3 examples here. So the first example is using the neural compute stick that I mentioned earlier. Right? And so people were able to take that, which actually is very, very cheap. It costs you $79, and they're able to build applications for skin cancer screening. And what they have done is they use the software Intel has developed, and they do training using different frameworks like TensorFlow and Caffe, and then they do inference using the OpenVINO toolkit that I mentioned a little bit earlier. Okay? So this is one example here. And the other example I have here is I mentioned recommendation systems, right? So Taboola is a very important player in terms of providing content recommendation engine. So they're serving over 360 billion recommendations to 1 billion unique visitors monthly. So their scale is really very, very high. Okay? So they actually have evaluated various different options they have, including CPU and GPU and so on, and they were able to get 2.5x speed up through software optimizations, and that actually eventually they decide to use Intel CPU for the work they have there. Okay? Now the last one I want to show you here is a cloud service provider. So JD.com is one of the main platforms for selling different kinds of things. They started out as selling electronics, and later on they branched out into all kinds of stuff they're selling there. So in this particular case, they have a Spark environment. They have a lot of data, and data is in Spark already. And so they just decide to try out the big DL engine we have come up with, and using that, they're very happy with the scalability results we have, and then decide to use the Spark environment, which is a lot of CPUs, to do deep learning there. Okay. Okay, to summarize, I just want to add, make a slight change to the pillars that everybody's talking about. So in addition to algorithms and data, on the hardware side, you really need both the best AI chips as well as the best AI software. And with that, we have some questions. Thank you.